So this first section of Chapter 5 is definitely considered a review section. This is material hopefully you've seen potentially multiple times throughout other algebra courses. But just as a quick review of the approaches that we can use when solving systems of equations, specifically right now, systems of linear equations. So the first idea we want to understand is if you're asked to solve a system, meaning a collection of equations, and you're supposed to solve it, the idea is you're treating those equations as all being rules that pertain to a specific x and y in this case. There's three ways to go about finding the solution to a system. You can graph it, or you can use one of the two methods, algebraic methods, called substitution or elimination. Graphing helps us give us insight as to what we're really doing when we solve a system. When you solve a system, you are looking for the xy pair that solves both equations, or, graphically speaking, a point that exists on both lines. Because in this case, for these two equations, and I went ahead and put some work in here to show this equation put into a graphing form. But with those two equations in graphing form, there are their graphs, and we notice that this point right there, the point of -3, 0, is the point of their intersection, and -3, 0 is the only xy pair that solves both this equation and this equation, meaning you can plug it in and it makes them true. So that's convenient. It's good to understand what we're doing, what we're kind of finding when we solve a system. However, nothing guarantees these graphs intersect at convenient places that we could find the coordinate. So this is one main reason why we're going to not use the graphing technique, graphing approach to solve them. However, again, just as a reminder, because we will see more graphs later on in this chapter, that is what we're doing when we solve a system, is finding the point where the lines intersect. So moving on to those algebraic approaches that we can use more often, we have one process called substitution. Here are the steps for them as I kind of walk through them in this one example, just as really a refresher. So it says solve one of the equations for one of the variables. It doesn't really matter which one. I'll just take this first equation and solve it for y. So it's 2x plus y equals -6. So I'll move that to 2x on over. The form doesn't matter. I'm not graphing it, so you don't need to think of this as needing to be in slope-intercept form. But there's my equation, my first equation, I'll call it, solve for y. So now I will take what y is equal to. Y is the same as this, and I will substitute it into the other equation in place of that y. So I'll have x plus 3 times, but now instead of y, I will have all of that. And that's equal to -3. And the goal here, the reason we do this is because now we're going to be dealing with an equation with one variable. So x, and distribute that, -18 minus 6x. I can combine a couple like terms, -5x minus 18. Add the 18 will give me a 15. Divide by a -5 will give me a -3. And then once you have your first variable, you go back and find your second. You can use either the original equations or you can use the equation you solved for initially because it will be in terms of the other variable, making it very simple to just plug in the -3 we just found. And it looks like there we're seeing algebraically that we're going to have the point -3, 0 as the solution to our original system. And again, you can absolutely check these very simply by taking those two values of x and y, plugging them into both equations, and ensuring that they do make both equations true. So that's the substitution method.